In Chapter 9, we are going to consider inferences based on two samples. So we're going to have two populations that are involved here. So with one population, we did confidence intervals and hypothesis tests. We can do the same thing here, except we're going to be comparing the difference here of two means or the difference of two proportions. And that can be in the confidence interval or the hypothesis test. So let's look at what our parameters would be here for a two-sample test. So if you're talking about the difference of means, you're trying to estimate the true value of mean 1 minus mean 2. That's keywords that would indicate this are things like mean difference or compare averages or difference in averages, and it's quantitative data. Difference in proportions, P1 minus P2, that's the parameter. So if you're looking at difference in proportions, difference in percents, comparing proportions, comparing fractions, comparing rates, all of those keywords are indicating difference in proportions. That is qualitative data. So for example, the proportion that are male, the proportion that are female, between two groups. So the difference in the proportion of males, for example. So let's look at the case first of two population means and independent sampling here. So if we have large samples, and that's the case where N1 and N2 are both greater than or equal to 30, then we can use the Z statistic for our sampling distribution. If we have small samples though, then we'll need the T statistic, T distribution. So if we take two samples here from two different populations, then our sample mean x bar 1 will approximate the first population mean, and then our second sample mean x bar 2 will approximate the second population mean. And then x1 bar minus x2 bar is going to be our estimate, our point estimate for the difference of the two means, mean 1 minus mean 2. So what about the sampling distribution then for x1 bar minus x2 bar? Well, just like in the one variable case, the mean of the sampling distribution is equal to the population parameter. That should be approximately equal to the population parameter. With independent samples, your standard error or your standard deviation of that sampling distribution, sigma x1 bar minus x2 bar, is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2, and then take a square root. Now if you don't know the population standard deviations, you can use the sample standard deviations. Now notice that this is it's kind of an average here. The square root here is going to actually undo the squares there, if you took the square root of this first term, you'd get sigma 1 over root n1. If you took the square root of the second term, you'd get sigma 2 over root n2. And those would be the individual standard deviations of the sampling distribution for x1 bar and x2 bar. So notice this is kind of a combination of those two standard deviations. And then by the central limit theorem, the distribution for x1 bar minus x2 bar, that's going to be approximately normal if you've got large samples. And again, large samples here mean that both sample sizes are at least 30. So if that's the case, then our large sample confidence interval for the difference of two means, mean 1 minus mean 2, is going to be your point estimate, x1 bar minus x2 bar, plus or minus a z value times the standard deviation of the sampling distribution. So we plug in here the sampling distribution for the standard deviation for the sampling distribution. We have this formula here. And again, if you don't know sigma 1 and sigma 2, you can use S1 and S2. But again, it's point estimate plus or minus z value standard deviation. Now the assumptions that we have for this are independent samples, so one sample cannot depend on the other, and from two populations, large sample sizes, N1 and N2 greater than or equal to 30, That's going to ensure that the x1 minus x2 bar distribution is approximately normal. And we also need that the sample variance is approximately equal to the population variance for both populations. So otherwise we won't be able to make this substitution. And then when you do a large sample hypothesis test, this will parallel what we did in one population. So if you have a one-tailed test, that's when your alternative hypothesis is less than or greater than. So your null hypothesis is going to be mean 1 minus mean 2 equals d sub 0. D stands for difference. Usually this is 0. So that if mean 1 minus mean 2 equals 0, that means the two means are equal. And then this one, if that's a 0, that means mean 1 less than mean 2. Or greater than, depending on which way this sign goes. For a two-tailed test, your alternative hypothesis is a not equal. And again, the D0, most of the time, that's a 0. That's the null difference is what it is. So either the populations are equal or they're not equal. So notice here again, mu1 less than mu2 means the difference is less than 0. Mu1 greater than mu2 means the difference here is greater than 0. And mu1 not equal mu2 means the difference is not equal 0. So those are just equivalent ways to write that. And then our test statistic, you're going to take the difference of the sample means minus the hypothesized difference, again, usually 0, and divide by the standard deviation of the sampling distribution. Again, you're going to use this one or this one depending on whether or not you know the population standard deviation. And then your rejection region is going to be z greater than z alpha or less than minus z alpha for one-tailed. And for two-tailed, it'll be z minus z alpha over 2 or z greater than z alpha over 2. Our assumptions will be the same as above as for the confidence interval. And then since we're using the z distribution here, we have some common rejection regions if alpha is 0.1, 0.05, or 0.01. So these are the same as they were for one variable.